Hi everyone, today we're going to be presenting a type of non-traditional machining called mechanical energy processes. As an introduction, it is the energy of motion and the energy of objects that move. It is produced by turning potential and kinetic energy into power. It is also the driver of renewable energy, so it is used to produce power or convert energy. There are different types of mechanical energy processes that we'll be going into today. The first is ultrasonic machining. There are also two different types of processes using water jets. The first is water jet cutting and abrasive water jet cutting, which are very similar. There are also non-traditional abrasive processes called abrasive jet machining and abrasive flow machining.
So why do we need non-traditional machining? This unique process takes advantage of the fact that there's no physical contact between the tool and workpiece. This non-contact nature allows manufacturers to work with very hard and high-strength materials such as ceramics, titanium, hardened steel, both efficiently and accurately. Due to the strength of these materials, standard machining processes would not be viable. It also allowed for more complex parts that require any holes or internal-external profiles which were very hard to achieve using conventional machining processes. The way these the way these processes were carried out also allowed manufacturers to avoid any damage to the surface that would often result from the stresses created by conventional processes. In summary, non-traditional energy processes were a total game changer for the industry. It helps allows engineers to work with a wider variety of materials, tackle complex designs, all while maintaining the structural integrity of the workpiece.
Hi, my name is Alex Padron, and I wanted to talk to you guys about ultrasonic machining. More specifically, I wanted to talk about the working principle of ultrasonic machining. The principle and process is fairly simple. The transducer provides the vibrations to a tooltip, and this tooltip is typically of a geometry that you would want to impart onto the workpiece or the work surface. So if you wanted a circular dimension hole, you would want the tooltip to be circular. Um, Apart from the transducer inducing the vibrations to the tooltip, there is a nozzle that lies in between the workpiece and the tooltip, and this nozzle provides the slurry, which is a combination of abrasive particles and water. And this slurry flows in between the tooltip and the workpiece. And as it's flowing in between, slowly and gradually impinges on the surface of the workpiece, thus imparting the desired shape or size that is needed. Another process that is important to consider are the parameters that affect the material removal rates of ultrasonic machining. The material removal rate is inversely proportional to the cutting area of the tool. The larger the area that's desired to be removed, the slower the rate of material removal. Another factor to consider that affects the material removal rate is the frequency and amplitude of the vibrations that's induced on the tooltip. Typically, increasing the frequency and the amplitude of the vibrations will increase the rate at which material is removed. And lastly, a very important parameter that affects the material removal rate is the type of abrasive particles that are used in the slurry, as well as their shape and their concentration, as this will likely affect the kinetic energy that is needed for the slurry to slowly chip away at the material.
Water jet cutting uses a fine, high-pressure and velocity stream of water impacting the material surface perpendicularly. In water jet cutting, the fluids are preferred to be polymer solution because it tends to form a coherent stream. As the diagram shows, the fluid goes through the tube and is ejected by the nozzle directly to the surface in order to make sure the pressure approaches maximum. There are several parameters that should be considered. The standoff distance between the nozzle and the surface is expected to be small to minimize the dispersion, but don't contact the surface. Change the nozzle opening diameter and the pressure of the fluid according to what material it is and how thick it is. These two parameters decide the rate of cutting feed, typically from 5 to more than 500 millimeters per second. Water jet cutting is usually automated using computer numerical control or industrial robots to control the nozzle unit along the trajectory we desire. In this GIF picture, we can see what it actually looks like. Water jet cutting is preferred to be used when the materials are sensitive with the high temperature. It can also be used on both hard and soft materials, such as the following examples. We can also see water jet cutting used in mining and aerospace areas to cut, shape, and rim the target objects. Abrasive water jet cutting is a branch of water jet cutting. As the picture shows, abrasive particles are added to mixing chamber after the water is injected from the nozzle. This method needs larger nozzle orifice diameters to let the abrasive pass through without blocking. Water, water pressure stays the same. Standoff distances are somewhat less to reduce particle scattering, typically 1/4 to half of those in water jet cutting.
Hi, my name is Mark Capula, and I'll be talking about the abrasive flow machining process of our project. So it's an interior surface finishing process that has an abrasive laden fluid that is being forced inside of a chamber that needs to be cleaned, which causes erosion and removes the hard surfaces inside. So it's a surface improvement in the inside of the material, so it polishes the inside. And from the left hand picture is the abrasive flow machining setup, and from this right hand picture is the before and after of the material when it goes, or of the part when it goes through the process. And as you can see in this right hand picture is the before picture, where it's the interior surface is rough, compared to this left hand picture, where the interior surface is smoother. To continue on abrasive flow machining, the methods for this is that there's a hydraulic pressure that is used to exert forces to allow the deformable gel abrasive to finishing on the working surfaces. And the forces present in these are the axial force, Fa, Fr, the radial force, and Ft, the tangential force, as you can see in this image to the right. And Fc is the total forces of the abrasive particle given in this equation right here.
Hello everyone, my name is Benjamin Viscondi, and I'll be going over the abrasive jet machining process for our project. This process is also known as microblasting and is somewhat like water jet cutting, which was previously discussed. However, with this process, rather than using a liquid solution, fine particles commonly known as abrasives are used. These abrasives are small spheres with a diameter of about 0.001 inches or 0.025 millimeters. Some examples of these include aluminum oxide, iron oxide, silicon carbide, and powdered iron. These minerals are introduced into a mixing chamber where it is combined with high pressure air obtained from a compressor. A vibrating bottom at the base will help the chamber to mix the air and particles thoroughly. Then once mixed, the two will be transported via a line to a nozzle, and then in order to create the blasting process, Bernoulli's formula will have to be used. This means that as the pressure decreases when leaving the nozzle, the velocity of the mixture will have to drastically increase. This high velocity abrasive will then hit the work material and begin to blast away any unwanted pieces or material through friction. Once this process is finished, the manufacturer will be left with a smooth finished piece. For abrasive jet machining, ratios of volume and mass flow rate play a major role in the process. In this example problem, it is stated that the ratio of volume flow rate of the abrasive and gas is 0.2. We need to calculate the mass flow rate ratio of the abrasive to the combined mass flow rate of the abrasive and the gas, or alpha in this case, given that the density ratio of the abrasive to the carrier gas is equal to 20. So as shown below, we know the ratios for both our flow rate and our volume. Combining these with the fact that rho times volume is equal to mass, we can manipulate the equations for that first part of the solution. So in order to get rid of our density A or rho A, you can divide out by rho G and then plug in 20. And then in order to get rid of our volume flow rate, what you can do is divide by volume flow rate of G, and you'll be left with 1, and then you can plug in 0.2 for that VA over VG. After completing all that, you'll be left with 4/5 or 0.8, which will be your final answer for alpha.
Each process has its different advantages and disadvantages. I'm going to first be going into the advantages of the applications. Ultrasonic machining has high precision. It has the highest surface finish available in all other processes. It also has low cost and high speed, so it uses minimal energy but has high production rates. It also easily cuts through extremely hard and brittle materials. Water jet cutting is considered green technology, meaning that it doesn't create any hazardous waste. It also has low operating and maintenance costs and has extremely high accuracy. Abrasive flow machining has the ability to control specific outputs using different grit sizes and types of media. It also has a high setup and quick change tooling and is fully automated and has fully automated system capabilities. Abrasive jet machining is suitable for non-conductive brittle materials, has low capital investment, and has good surface finish and can be used to cut intricate holes and shapes. Each application also has its disadvantages. To begin, ultrasonic machining can't be used on soft materials. Its cutting tool has a quick wearing time, meaning that each time it has to be changed, it causes a lot of waste. It also has high power consumption, which leads to high cost. Water jet cutting has slower cutting times, meaning lower production rates. It is also difficult to machine hard materials and has high starting cost. Abrasive flow machining has the disadvantage of surface integrity with low surface finish. It also has high machining times. Abrasive jet machining is not suitable for soft and ductile materials. The abrasives used are also not reusable, so the collection and disposal of the abrasives is problematic and also requires lots of cleanup. It also has limited nozzle life due to quick nozzle wearing, meaning that it causes waste because of the changing of the nozzle.
Our final 380 project helps us dive deeper into mechanical energy processes and discover what these non-traditional processes are and how they work. In summary, these techniques offer diverse capabilities to meet the evolving demands of modern manufacturing. From each of the four methods we discussed, such as ultrasonic machining, water jet cutting, abrasive jet cutting, and machining, along with abrasive flow machining, each have its own strengths, unique set of strengths and applications. Take the ultrasonic machining, for example, which help achieve accurate and precise cuts, which are well suited for hard and brittle materials like ceramics and glass. The high-frequency process allows for intricate cuts to be made that were almost nearly impossible before. Then we have water jet cutting. This versatile process utilizes the high pressure of water as it flows through a jet to cut cleanly through material without inducing any heat effects, thus not providing any risks to the structural integrity. Then we can also add abrasive to this process to cut an even harder material, which would allow more variety of materials to be used. Next, we have abrasive jet machining, which operates similarly to the water jet cutting. However, it's used an abrasive gas mixture that can be used in both cutting and finishing operations. Lastly, we have abrasive flow machining, which offers a unique approach to finishing complex parts by using a semi-solid abrasive, which can polish and burr hard-to-reach internal passages or intricate shapes. This process is particularly valuable for achieving high precision surface finishes and ensuring the quality of complex components. So whether it's achieving precision cuts and hard materials with USM, providing clean cuts with AWJC, or achieving high precision surfaces with AFM, these processes are shaping the future of manufacturing by offering innovative solutions to complex machining challenges. Thank you.